Well, hello and welcome to Mr. Robinson back here with yet another brand new exciting video, all math based of course, and as always it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Stepping inside, as we have now concluded Chapter 2 in the Big Ideas Math Integrated Math 3 textbook, we are in the Chapter 2 review, getting good problem set evolved sections 2.1 to 2.7 with linear and quadratic functions. Some of them are absolute values. We do some graphs, we solve some systems, we model some data, we transform some equations, all this and that. And they got some examples with you before each problem set in the section. If you want to check out this PDF down below, you can download it in the description section here, down below. And you can also find the timestamps for each corresponding question and where each section begins. You can also download any provided graph paper that I will be giving you. Without further ado, guys, I'm going to go ahead and I'm going to get started. We're going to look at section 2.1 to begin with, where they it's called parent functions and transformations. So all the individual parent functions for constants, linear equations, absolute value equations, and quadratic equations. Basically, y equals 1, I think, is the parent function they use for a constant, one that just goes across like that. Y equals x. Y equals x is for linear equations. Y equals absolute value x, absolute value equations. Y equals x squared for quadratic equations. These are the basic ones pre-transformation that they use for any of these instances, and then we will transform these. We'll either do translations, vertical stretches and shrinks, horizontal stretches and shrinks, and any sort of reflections as well. That's what we describe. So in getting rid of that, let's see how they talk about this one. This first example they have before we start this actual problem is graph g of x equals x squared, x minus 2 quantity squared plus 1, and its parent function. So the blue one is g, and the black one is the parent function f. So this is the x squared. Keep in mind this is that 1, 1, 2, 4, 3, 9 starting from the origin, so no real change in that. But g is a change. What kind of change is it? Well, g has a vertex of 2, 1. I don't know if that's something we learned at the time, but we know it now as a for sure to just mention. It's at 2, 1, and when you see that comparison to this one right here, stretch factor is still the same, so the only two differences were translations to the right and upward. We translate 2 units right and 1 unit up, and that's what they're talking about here. So that's what's going on g of x in comparison to it. Now, the way that we know that is things inside the function you got to treat opposite of. If it says a minus 2, means you go 2 to the right. If it said plus 2, it means you go to the left. If it had a 2 times that means you got to take half of your x values, things like that. And outside of the function is where you affect y values, and they stay as they are. When you see a plus 1 outside of the function, you go 1 up. If I saw times 3 right here, it'd be a vertical stretch by a factor of 3, all that kind of stuff. So this is the only example that they provided, so I'm bringing those up in case they come up in our set, or in case they don't come up in our set, right? The whole goal is for you to review the chapter. So let's see which ones we have to do. Graph the function and its parent function, then describe the transformation. Let's start with number 1. We got f of x equals x plus 3. Now keep in mind, this is the transformation of its parent function. The parent function, in my case, or in this case, would have probably been y equals x. So let's take one of these graphs here. Let's make the y equals x equation, the parent function, and then we'll make this guy here as well. So the parent function y equals x is basically in y equals mx plus b form, a slope of 1 and a y-intercept of 0, which means it kind of has this diagonal look to it right here, that 45-degree angle crossing through the origin. That's the original parent function. I can't really call it f because this one's called f, but let's look at f of x equals x plus 3. Now f of x equals x plus 3 has a y-intercept of 3, and a slope of 1, so up 1 over 1. And I do recognize that, yes, I am indeed graphing this based off my own knowledge of graphing linear functions without talking about the transformations themselves. But for the time being, because we've been practicing graphing these ones, and because some of them, they're going to rely on you to make a table or graphing calculator, I am going to base it off that knowledge. This one, I do believe this is how they do it. They have you graph it and then describe the transformation. It's literally how they say it. But if you wanted to, you can compare y equals x to y equals x plus 3. And the difference is 1 has a 3 added to it. How does that 3 change things? It's a vertical translation. The graph of f is a vertical translation 3 units up from its parent function. So what's happening is every point is just 3 units higher than its original point on the parent function itself. So we're talking about from the origin, we're 3 units up. From this random point, we're 3 units up, etc. 3 units up, 3 units up, That's what the translation is. I can literally take this and go up 1, 2, 3. And that's all that it is. There's no other change than that. There's no reflection, yada, yada. I'm sure we're going to hit some, but not in this one. That's number one. Number two. Number two, we have g of x equals absolute value of x minus 1. And once again, there's a simple single transformation taking place. So let's check out what that is. Okay. So the original parent function for this is this belongs in the absolute value family. And I note when I say the word family, I'm realizing parent, hey, there's a parent function in the family, and the parent function is y equals absolute value of x. Now the absolute value of x is kind of like y equals x. It's got an up 1 over 1 slope. The difference is the absolute value of negative numbers are also positive. So instead of going down and to the left, it's going to go up and to the left, right here. It's got a V-shaped look to it. It's got a slope of 1, and then the other side negative 1. But this is the basic parent function without any transformations. Vertex is at the origin. I'm going to change that to black in a second. Vertex is at the origin, and it does that. This is in a non-transformed way. Well, we have one that's transformed. Okay, we have one that's transformed, absolute value of x minus 1. If you consider the description of what happens first, the minus 1 is outside of the function. It's affecting your y values, making everything 1 lower. So it's basically taking this function that you see right here, and it's transforming everything 1 unit down. So if you wanted to describe it first, and then graph it second, or get the description to make the graph, we could say take this and translate 1 unit down, and this is what our graph's going to look like. So I am going to go ahead and get this graph done first, and I'll show you how to do this graph as a result afterward. But the graph of G is a vertical translation 1 unit down from its parent function. Now, if you wanted to do this one yourself, again, the way the absolute value functions work, they're going to work kind of the same way that you do quadratic functions in the future. But your equation is some y equals a times x, absolute value of x minus h plus k. We're looking for the vertex of our guy here based on h and k. Because I don't see anything within x, that means h is 0. So for your vertex, the h value is 0. Plus k says minus 1. That means we're adding negative 1. So your vertex is at 0, negative 1. This is where I'd begin my graph. This is, again, assuming you're not using a table. If you want to use a table, just plug in points and see what you get. But I would start from that vertex. And then my a value also is 1, which means there's no change in vertical stretch. The slope is 1. We do up 1 over 1, up 1 over 1. And that's where this thing goes here. And it goes the same way in the other direction. If a was negative, the graph would be flipped over in an upside-down V-shaped fashion like that. But that should complete this problem. And it is, again, translated down 1 unit this time. And you literally saw me do that to make this actual graph itself. So that's what we're doing there. That is number 2. All right, number 3 is a quadratic function. You have h of x equals 1/2 x squared. This is the one where, once again, I know that we're in section 2.1 when we're talking about this. I know at the time the book was still using tables. At some point they stopped. What was it? Section 2.5? Whoopsie. I think it was section 2.5 that they stopped using tables. And in those instances, no. I'm trying to copy this graph. Give me 1 second. Copy. Can you process that? There it is. Awesome. So I think they stopped using tables at that point. But I never used tables. So understand that a quadratic function means we're squaring our x values to get our y values. The original parent function, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. You hear me say all the time, 1, 1, 2, 4, 3, 9. And squaring negatives also turns them positive. So the original parent function, y equals x squared, would look like this. It is a parabola. It's a U shape instead of a V shape. There's no constant slope. This has a stretch factor of 1. That doesn't mean a slope of 1. It just means you take your values, you square them, and you leave them as they are. But this one, this h of x equation, has a vertical compression factor. This 1/2, and there's no change in vertex, right? There's no translations, horizontal or vertical. This is just about the stretch factor, or compression factor, or as they probably say, shrink factor. This has a vertical shrink. Everything will be 1/2 the heights that they previously were. And this is a nice problem to do it with because there is no translation and we have the parent function. This is a nice way to show exactly what it is I do with this kind of graph, even if I don't graph the parent function. This time it's graphed, so let's check it out. 0 squared is 0 times 1/2 is 0. We're staying at the origin for the vertex right there. After that, 1 squared is 1, but we got to take half of 1. We get 1/2. This is literally what you do in your table as well. 2 squared is 4, half of 4 is 2. We are shrinking our heights to half of what they originally were. Half of 1 is 1/2, half of 4 is 2, half of 9 is 4.5. And I plot that one here. So I'm equating this to that one. I'll show you with arrows in a bit. And I can do the same thing on the other side. But don't be mistaken in thinking that that's all we can plot on these ones here. We ran out of window range on black because 4 squared is 16. We couldn't fit it. But I can fit half of 16 on here. Half of 16 is 8. And this is where people might confuse the graphs for being, they might say they're wide. So like, for example, if I don't graph that yet, maybe I just plot this and I show it like that and I say, okay, I'm done. And then you can totally tell it's just a vertical compression. We're taking our values and shrinking them down. We're pulling them down. But I always plot as many points as I can fit. So I'd like to fit 4, 8 on this. Remember, 8 is half of 16, 16 being 4 squared. So I want to plot that one. And the only problem with doing this, not really a problem, is your perception is suddenly, it's not about vertical compression anymore, but about horizontal stretch. If I asked you to compare one graph to the other, you might say, oh, the blue one is wider than the black. Well, it is wider than the black, but it's only because we graphed those fourth set of points that you saw that. But what if I graph the black one all the way up to 4 squared? Now suddenly you might not say it's wider, but it's shorter or something. I don't know. Depends on how you see it. It is wider, but we're talking about the vertical compression, and that's how I'm going to describe that thing. This one here compressed 1/2 or 1 to 1/2, 4 to 2, and 9 to 4.5, right? It brought these ones downward. That's the idea. So this graph of H, the graph of H, is a vertical compression or shrink by a factor of 1/2 from its parent function. And that's the only thing that's happening on this particular problem. Okay. All right, number 4, and I'm glad that I brought up the constant one that we had before. So number 4 says h of x equals 4. Now you'll notice there's no x in this. That means that, well, it means several things, but this is a constant function. The only thing that's affecting it is nothing. Y is 4, is what they're saying. Now the original parent function would be y equals 1, so I do have to bring that up. The original parent function would be y equals 1. I thought it would be y equals 0. The book kind of says y equals 1, so we'll go with that. Y equals 4 looks like this. When I said that nothing changes it, or I don't know how I said it, nothing affects it, what I mean is that no matter what x is, y is always 4. So here's the original parent function, here's the new function. How do we go from one to the other? It's a vertical translation, 1, 2, 3. You could also say it's 4 times taller. I think there's more than one way we can describe it. I assume because it's a constant we're talking about, it's more about the addition of, because it's not multiplying by an x. Because x is not there is what makes it constant. So anyway, we're going to say that it's a vertical translation 3 units up from the parent function. So the graph of h is a vertical translation 3 units up from the parent function. Okay. That's all I'll kind of say on that one. There aren't many constants they throw into the mix. I did not even change this to number 4. That's how little I think of it. No, but yeah, that's what we're doing for that problem. I think it's the first and last time we're going to see one like that. Not that we won't see constant functions again, but just describing transformations. Don't expect too many of those. Okay, let's move on to number 5. Now, numbers 5 and 6, it looks like we're going to have multiple changes to them. And the first of new changes that we got to talk about is this negative in front of our function. F of x equals negative absolute value of x minus 3. So this is an absolute value function. We saw its parent function previously. I wish I could copy and paste it. I could, but I don't want to go back and bog down that time. Let me just graph it as I talk on this thing. So absolute value of x minus, or negative absolute value of x minus 3. We've seen the minus 3 before as a vertical translation. And heck, when we talk about this thing, I'm going to talk about the translation first when it comes to me graphing it. And I don't think last time I graphed this one first, so this time I will. My vertex is at 0, negative 3. We remember that the h value of 0 means there's nothing inside with x. You'll see on like number 6, there's something inside the function. That's when we do horizontal translations. This one doesn't have that. So 0, negative 3. So I start with the translation when I graph. That doesn't mean when I describe it, I start by describing translation first. And there's a big reason why. When I graph this thing, I'm going to do everything in relation to my vertex, which means I already know that everything will be subtracted 3 down. I'm pretty much pretending like this is my new origin, my new 0, 0. What I am going to do now is flip everything over. This thing is a vertical, it's a reflection in the x-axis. That means flipping it over this way. They're saying take this graph right here and flip it over. Make it from that to that. We make it from that to that, we shift it 3 units down, so my graph is going to look like this. So I acknowledge that I'm at my translation already, and I acknowledge that it'll flip over with a slope of 1, so I'm going to go down 1 over 1 this way. That's what the negative means to you in a way. Slope of negative 1, or take whatever your parent function had, a slope of 1, and make them negative, which is what we'll do there. So that's what the graph will look like, and then we'll describe it. And when we describe it again, make sure you describe the reflection first. If you describe the translation first, and then you say reflect it, then technically the graph would actually flip over and go up 3 units. So we have to make sure we describe the reflection first. So the graph of f is a reflection in the x-axis from the parent function, followed by a translation 3 units down. So those are the two things I want to describe, one and then the other. And if you're not sure, you're like, how do I know which order to do? Always go to me, left to right of your function, assuming it's in your vertex form or your preferred form that you like to see it. I think mostly vertex form or slope-intercept form. But go left to right with the letters A, H, and K involved. You can go alphabetically, a lot of things like that. If they describe it in a different order, like translation first and such, you're going to note that with your order of operations. I think we'll run into some of those problems when we get there. I think that's a different section, though. It might be section 2.2. Number 6, g of x equals negative 3 times x plus 3 quantity squared. Once again, this was at a time that they probably assumed you were graphing using a table. Never assume I'm going to graph using a table. And in this case, I'm going to do probably the graph first, and then we'll get to the transformation after. So the original function again with an x squared, 1, 1, 2, 4, 3, 9, and reflect those points over here like that. And here's the parent function. The new graph here, this is in vertex form. Let me write out what vertex form looks like for quadratics. It's a lot like the absolute value, only it is a quadratic. It's an x squared. So it's a y equals a times x minus h quantity squared plus k. It's called vertex form because the vertex is at hk. Now, if you'll notice, this is x minus h says x plus 3. That means your vertex is at negative 3. And then nothing is added right here. That means that's 0. So negative 3, 0. So I'm actually going to start this right here. That also includes a translation 3 units to the left. I probably won't mention that first, though. I want to mention everything about negative 3. Negative 3, the negative is in reference to a vertical, I keep saying vertical, a reflection in the x-axis. And then the 3 is in reference to the stretch. It's not a slope, but it's a stretch of this thing. Everything's going to be 3 times larger than it was. So instead of being up 1, it'll be up 3. Instead of being up 4, it'll be up 12. You got to multiply everything by 3. It's going to be 3 times taller like that. Only it's also going to be flipped over, and it's going to be over here. So this is the kind of graph we're going to look at. I'm going to go ahead and graph that all right now. So instead of going, as I would say out loud, 1, 1, 2, 4, 3, 9 upwards, we're going to do it downwards, and we're going to triple those values 1, 4, and 9. So over 1, down 3 instead of 1. Over 2, down 12 instead of 4. This already can't really fit, but I'll go ahead and pretend like I could. Plotting them anyway. We're not talking yet about axes of symmetry for these quadratics. I'll do that later in section 2.5 because, again, they assume you're using a table at this point, but we reflect across the axis of symmetry. It's the first time we're seeing a translation off of the y-axis going this way, so it's the first time I even want to bring it up. Anyway, there's the graph. Let's go ahead and describe it. The graph of G. The graph of G is a reflection in the x-axis and a vertical stretch by a factor of 3, stretch, from its parent function, followed by a translation 3 units left. To the left. There we go. Okay, and that completes section 2.1 with respect to the questions they wanted to ask. I know they had different kinds of questions, I forget what they were, but this did cover all of the constant, linear, absolute value, and quadratic functions. Okay, 20 minutes in, let's go to section 2.2. Now, before we hit numbers 7, 8, and 9, let's look at the examples that they provide for this. This is exactly what I was talking about with respect to doing multiple transformations. Transformations of linear and absolute value functions. We save quadratics of this set for, I think, section 2.5. But the same kind of thing will occur then. Let the graph of g be a translation 2 units to the right, followed by a reflection in the y-axis of the graph of f of x equals absolute value of x. So here's our parent function. They're going to say write a rule for g. Now what they're going to do in this scenario is they're going to take your... They're going to use different letters. They're going to eventually get to g, but they're going to have an interim letter h of x, to just do the first thing they're going to say. Translation 2 units to the right, followed by a reflection in the y-axis. Now, normally they do it the other way, right? Normally you see reflections and stretches happen first and then translation second. That's how I said that we should describe ours in a basic form. These ones had that basic form. However, this one's going to be a little bit different. This one's order of operation changes because we're doing the translation first. If I translate something 2 units to the right and then I reflect it over the y-axis, it goes the other direction. Instead of 10,000 paces east, you're going 10,000 paces west. You know what I'm saying? You got to go all the way back to what we're doing. SpongeBob reference, by the way. Quick note, I don't know how often these days that I say a SpongeBob reference in class or something like that, and I go, you guys know what I'm talking about? And they're like, my mom and dad wouldn't let me watch SpongeBob as a kid, which is quite interesting. It seems like over like 50% of students would always say that. Anyway, I don't know if that's true for you guys. Anyway, SpongeBob started for me when I was in 6th grade. Anyway, this is still the example, right? We're going to translate 2 units to the right, and if you've seen so far a couple times, number 1, it's inside the function. Number 2, it's the opposite effect of what you see there. To go 2 units to the right, that's 2 units to the right on x. They become 2 bigger. We got to compensate by subtracting 2 on all our values. So we do opposite. So the kind of function is absolute value of x. So x minus 2 replaces x in this function. Instead of f of x equals absolute value of x, it's f of x minus 2 equals absolute value of x minus 2, and we're calling that guy h of x. We call it h of x to make it a lot smaller looking. The next time we're going to do something with g, which is followed by a reflection in the y-axis. Now, a reflection in the y-axis is actually affecting x values. Instead of making your function negative, we're making things inside the function negative. We're making our x's negative of our newly transformed function h of x. So we're now going to substitute negative x in for x in this function right here. That's where it goes in place. So instead of absolute value of x minus 2, it's absolute value of negative x minus 2. Now they do a couple other steps which are both interesting and things that I would do, which is factoring the negative out of here. Now I would factor any number out in front of x, positive, negative, anything that's not 1. I'd factor it out because if I want true vertex form of this thing and I want my true translation of what this thing is going to be ultimately, I got to get it pulled out. And I don't want to overspeak on this. I did it in the section at the time, but general rule is factor that thing out. It's a negative 1. Negative 1 times the quantity x plus 2 can be separated as 2 separate absolute values. The absolute value of negative 1 is 1, and all you're left with is absolute value of x plus 2. We'll see if this ends up happening for us. It did in the sections at the time. So if you check out section 2.2, you might find some questions like this where this happens. Bottom line is, this is the transformed function g of x. So if you see that as kind of like a quick graph version of what that is, keep in mind the original function would have been right here, just absolute value of x like that, right? They said it would have gone 2 units to the right, 1, 2, and then they say reflected across the y-axis. So reflected across this axis means flip this thing over, literally in and of itself, just turn it this way, which should actually mean no change, unless my drawing is off. But it also goes from 2 units this way to, boom, 2 units that way. And that's the idea of where this thing ends up. Does this follow along with our equation that we have? Yes, because this has a vertex of negative 2, 0. Remember, the plus 2 means it's opposite of what we have, and that's indeed what this thing is right there. So this thing does agree with it, noting that doing the translation and then reflecting is different from reflecting and then translating. If I took my graph, and reflected it first, reflecting would literally make no change. I mean, it might make a slight change in how it looks, but it'll make no change right there. And then if I went 2 units to the right, this is where we'd end up. And there's a difference between making x negative first and then doing the -2 versus doing the -2 and then making x negative first. Anyway, I wanted to call attention to all that there. Let's go ahead and forego that stuff, and let's go to our official problem set. Let's go to numbers 7, 8, and 9 with that stuff in mind. I have a lot of room here. Number 7. Well, let's look at the instructions first. Write a function g whose graph represents the indicated transformations of the graph of f. Use a graphing calculator to check your answer. Well, look at me. I am the graphing calculator now. F of x equals absolute value of x is the original function. So parent function. We are going to do a reflection in the x-axis followed by a translation 4 units to the left. Now, I'm fine with doing both of these one at a time personally because it's not disrupting the order of operations flow. We're used to doing reflections and stretches first and then translation second. So g of x is going to take the original f of x equation, only it's going to do 2 things to it. For one, it's going to reflect in the x-axis. That means an effect on y. That means we're going to be making these negative. The second thing is we're going to translate 4 units to the left. So inside of the function, we are going to be adding 4 because our x's need to be 4 less than they were before. So the opposite of f of x plus 4. So what we're going to do for g of x is, and you might know how to do this just based off reflection, do all this, I can use my vertex form. Okay, that's fine. But now we're going to substitute. We're going to take the opposite of our function, so negative, boom. And inside the function, instead of x, we'll be writing x plus 4. And that'll actually be it, right? That's all we do there. Now, my confirmation with the graphing calculator, or look at me, I'm the graphing calculator now, is the original function was right here in blue. F of x equals absolute value of x. Let's take this thing. I'm going to kind of copy paste it, make it a different color. I'm going to take this thing. We're going to flip it over. Okay, pretend like we reflection in the x-axis. Boom, like this. Hold on, it's not moving. Can you move for me, please? There we go. Reflection in the x-axis, followed by a translation 4 units to the left. 1, 2, 3, 4. And it looks like that. Now, whenever we do these, the general appearance... Ooh, something happened to my stuff. I'm going to probably pause in one moment. You can see I have my mouse cursor instead of my actual ink tool, which is a little weird. Anyway, so right here, this kind of mimics what we saw right here, right? I expected this, as far as my understanding of graphs, to have a vertex of 0, -4, -4, 0. And it does, boom, right there, and then a slope of down 1 over 1. So that seems to agree with what we have. So the graphing calculator right here pans out. Give me one moment. Okay, I believe I resolved my issues here. As you can see, this thing is now back. Whee! Okay. All right, let's jump to number 8. Once again, we're using the absolute value function. Remember, this whole section was only on linear and constants, so you only have one of 2 options. I think they really want to test absolute values more so, because linear is just slope-intercept form stuff. But looks like we'll do a linear on number 9. Quadratics are saved for section 2.5. So f of x equals absolute value of x. We are going to... Oh, and I didn't mention this stuff here. I'll bring it up this time. Vertical shrink, I call vertical compression by a factor of 1/2, and then followed by a translation 2 units up. Okay, so this one also seems to be in proper order, which means I can use this kind of in a one-step bit right here. So g of x equals, we're going to take 1/2 times our f of x equation, because it's vertical compression, and then we're also going to go 2 units up, which is also outside the function. Only things inside the function are those are the horizontal components that are changed: reflections, stretches, compressions, and translations. So these are outside. These are vertical. Vertical, vertical. So we're going to take our absolute value of x. We'll do 1/2 times absolute value of x plus 2. I mean, that's straight up what it is. We can confirm this, you know, if we graphing calculator or whatever. But basically that's what's happening, right? Instead of a slope of up 1 over 1, it's up 1 over 2, or up 1/2 over 1. That's vertical compression. 2 units up, everything gets added by 2 later. So instead of your graph looking originally something like this, now it's going to be 2 units up from there. Well, it's going to be half of what it was, vertically compressed, followed by a translation 2 units up. And this probably agrees with that look. Our vertex here is at 0, 2. And then you go up 1 over 2 instead of up 1 over 1 from there. Okay, let's go to number 9. On number 9, the original function was f of x equals x, the linear function, basically y equals 1x plus 0. But what we're going to do with this thing, we're going to translate 3 units down, followed by a reflection in the y-axis. So translate 3 down, and then reflect y-axis. Now, this seems opposite of what we would normally do. This is why it's safer to potentially wrap something around parentheses first or do them in different order or whatever. If you saw in the notes, in the example that they have, they did some h of x first, and I'm going to do that in the interim as well. H of x, it's not really a requirement for this problem because of reasons I won't talk about until the end, but here it's probably safe to do that. If we're translating first, and then we do one and then the other, let's start with this one. Now, translate 3 units down means you take your f of x and subtract 3 from it. That means f of x being x, we're going to do x minus 3, like that. And then after that, we can go to our g of x, which is a transformation of f of x, or h of x, I should say. Our h of x, we're going to reflect in the y-axis. Reflection in the y-axis is flipping over that way, I should say, which means we're making our x's negative. We're changing those ones instead of changing the y's. So instead of x, wherever we see our h of x equation, we're going to turn into negative x. Instead of x minus 3, it'll say negative x minus 3. Now you can see it didn't seem to change the vertical translation of negative 3. If it was reflection in the x-axis, yes, it would have turned this into that, and it would have been a plus 3. That's not the case here. So that's why I was saying it had no real effect on that. So if you knew that you could do these at the same time, awesome. I would definitely be cautious, though, still, and do it that way. So if you know anything about these graphs here, you'll know that, slope-intercept form, the original function was y equals x, just like this. Boom. Now what technically happened to this guy right here, let me do another one in green as an overlay. What technically happened to this guy right here is we translated 1, 2, 3 units down, and reflection in the y-axis means it's going to flip over like this. Boom. So it's still translated 3 units down, but it flipped over the y-axis like that, and that seems to be the negative x minus 3. It's got a y-intercept of negative 3 and a slope of down 1 over 1. So that seems to agree with that one as well. That is our number 9. All right, let's go to section 2.3 on modeling with linear functions. This is where we did a lot more things in word problems. We did scatter plots. We wrote things out in slope-intercept form or point-slope form based off our values that we had. Let's look at some of the examples. I think the one example that they have here, it's a pretty long one, but the table shows the numbers of ice cream cones sold for different outside temperatures in degrees Fahrenheit. Do the data show a linear relationship? If so, write an equation of a line of fit and use it to estimate how many ice cream cones are sold when the temperature is 60 degrees Fahrenheit. Now this phrase, line of fit, there are two different phrases. There's line of fit and line of best fit. Line of best fit generally says let the calculator do the work for you. Line of fit generally means we're going to do the work for ourselves and rough it out as best as we can. We're going to come up with our own equation. It's a little open to interpretation, meaning no two answers will be perfect, but they should all be within the same ballpark of each other, especially when we estimate how many ice cream cones are sold when the temperature is 60 degrees Fahrenheit. Okay, so we have the temperatures x and the cones y, and if you did enough stuff here, you might notice that there's not a perfect linear relationship here. The correlation coefficient is not exactly 1, okay? But it's close enough. When you see these points on the scatter plot right here, you can see they closely, this is before the line is drawn, that they closely make a linear relationship, and you can kind of draw a line that goes through them, which is what they're about to do. So step 1 is create a scatter plot of the data, plot these for x, these for y, and see where they pop up. The data shows a linear relation. The data, plural, show a linear relationship. Step 2 is sketch the line that appears to most closely fit the data. One possibility is shown. As we said, it's open to interpretation. Do the best you can. If I did my own, ballpark. It's about the same thing, right? So do the best you can on that. Step 3, choose 2 points on the line. For the line shown, you might choose 70, 117 and 90, 147. Notice that they actually chose 2 points that were in your data. That is not a requirement. I think what they did was they said, when we drew our line, it looked like it hit through these points pretty well, and I can't tell any other points that are hitting through pretty well, so I'm going to go ahead and choose those 2. That's kind of what they're saying there. Whoopsie, don't know what the S is for. The S stands for hope. So they chose those 2 points, and then step 4, they're writing an equation. Now, how do you write an equation based off of 2 points? You come up with, this is a line, a linear equation. So we need the slope and we either need to use a point or the y-intercept. Because we don't know what this y-intercept is and we don't want to guess, we're going to do this more based off of point-slope form. Point-slope form is y minus y1 equals m times x minus x1. Now, we need m first to make any of this happen. So m is slope. We need the rise from 70, 117, and the rise over run from 70, 117 to 90, 147. From 117 to 147, that's a rise of 30. From 70 to 90, that's a run of 20. And that reduces to 3/2 or 1.5. This is the slope that they're using. Do they ask us to interpret this data? They don't. So let me interpret that for you. 1.5 is stating every 1.5. Okay, I'm going to use 3, the 3 over 2. Every time the temperature increases 2 degrees Fahrenheit, you are using 3 more cones. What does this have to do with? Oh, how many cones? You're selling 3 more ice cream cones every time the temperature rises another 2 degrees Fahrenheit. It's getting hotter. More people are going to buy, basically. Anyway, so there's your slope of 1.5, and then you choose a data point that's on your line. We have 2 such instances we can use, this one or this one. So they choose 70 for x1 and 117 for y1. It looks like they put it in slope-intercept form. Is that a requirement? No. Is it recommended? Probably. So they distribute the 1.5 and they add 117 over and they get y equals 1.5x plus 12. And I want you to note that if we have to do this, I don't always get as clean of numbers. It depends on if I choose numbers that are perfect enough for it. Because they made their own example and used it this way, forced it in, they got clean numbers. I might not get clean numbers. So a y-intercept of 12, if I were to interpret this, means if the temperature was 0 degrees Fahrenheit, I'd still sell about 12 ice cream cones. Is that true? I don't know, maybe, maybe not. You have to understand that this data outside of the data points we have is considered to be an extrapolation. It's a prediction of stuff outside of what we've seen before. So sometimes when it's unprecedented, it's not sure if that's always going to be true. But we have an equation and we are going to interpolate data. We're going to find out and estimate the number of ice cream cones sold at 60 degrees Fahrenheit, which is within our data. That would be about right here. 60 degrees looks like it'll be about 100 cones sold. Let's see what happens when they plug it into this. 1.5 times 60 is 90. 90 plus 12 is 102. So approximately 102 ice cream cones are sold when the temperature is 60 degrees Fahrenheit. I just guessed based off the line that they drew, but they have the actual numbers. That's what we're going to use as well if we do these questions. Sometimes the chapter reviews don't actually do those questions, though. They just use the example and say, that's something, and it covered a lot. It didn't cover interpretations. I did some of that with it, but it did cover point-slope form, which is good because we haven't seen that yet together. All right, let's go ahead and jump to some of these questions. It looks like number 10 might be similar to what we just did. So you might need a graphing calculator. Well, I don't know if we're doing, oh, yes, it says use a graphing calculator. So get your graphing calculators out. If not, follow along with me. The table shows the total number, Y, in billions of U.S. movie admissions each year for X years. I like the information. Use a graphing calculator to find an equation of the line of best fit for the data. Notice they do say line of best fit, and we are going to use graphing calculator. So I'm going to plug these numbers in for X, these numbers in for Y in a graphing calculator. I have mine pulled up. Let's get it ready to go. So here, I'm going to hit Stat and Edit. This is something if you followed along with me before and you have a Texas Instruments calculator, you can do the same. These are my X values, and these are my Y values. I forgot because my calculator resets itself each time. I'm going to have to turn something on here. Dialog, diagnostic on, and stat plot, plots on. Okay, let's first look at the relationship of these values. It goes from 0 to 10 on X and between 1 and 2 on Y. So I'm going to go like from 0 to 10 on X and 0 to 2 on Y and look at this data. So there's the data itself, right? These are the points. They slightly form a linear relationship. I believe it. Now, you can draw a line of best fit through this thing as well. What I have to do is go to Stat and Calc, and I have to go to lin reg ax plus b. It's drawing a linear regression line in this y equals mx plus b. They say ax plus b for this thing here. And it's going to approximate the best line that would go through these data points here. So we're not drawing our own. They're making one for us. So this slope, 0.03457, I mean, I don't know how exact I have to be. I'm going to get a little bit big like that. So y equals 0.03457x, I'm going to put, plus, and I'll put 1.23. 1.23 is the y-intercept. The more slope values I put, the better off I am. Now, this has an r value of 0.97988. That's very strong. It's not the strongest we've seen, but it's very strong. That means that this line very closely fits your data right here. This is called the correlation coefficient, and it's positive when the slope is positive. The closer it is to 1, the stronger your data is. I don't know if we have to interpret that stuff, so I want to make sure to say that. Now, I just wrote this equation right here on my thing. I know that there's nothing else I have there yet, but I'm going to go back to the graphing calculator, and I'm going to type that info in to my y equals equation. So I'll put 0.03457x plus 1.23. Now this on the graph, see how that line very well draws through those points? That's kind of what we were trying to do. So that's our linear regression line. Let's see what else we have to do on the problem itself, though. Use a graphing calculator to find an equation for the line of best fit. Okay, that's all we had to do. That's all we had to do. Now, there are other things we could do with this information. They could say something like, use this information to estimate or predict the number of admissions y after 15 years, in which case we'd plug in 15 for x. Now that I have it in my calculator, I could even do it in the table. I could go into, I could ask values here, and I could say, okay, 15 years in, I predict, oh, this is y in billions of dollars, by the way, that the movie theater admissions, whatever, would make 1.75 billions of, is it billions of dollars? Billions of admissions. 1.75 billion admissions 15 years after this model started, right? You could also do things like interpret the slope and y-intercepts. Now, the slope of this will be kind of harder to say because it's in billions, but every year you're increasing, let's see, I think that's 100 million. You're increasing about 345 million. I said 345 34.5 million people every year is the increase in average movie admissions. The y-intercept would indicate that at year 0, which isn't the exact value because we have 1.24 instead of 1.23, but the model predicts that at year 0, when we started tracking, there were still 1.23 billion admissions in that year, so to speak. Anyway, that's a lot of the different things we can do on those. And remember, this is a chapter review. There may be questions that they're asking here, but I want to make sure to cover as many things as possible for you. Number 11, you ride your bike and measure how far you travel. After 10 minutes, you travel 3.5 miles. After 30 minutes, you travel 10.5 miles. Write an equation to model your distance. How far can you ride your bike in 45 minutes? Now, those are two different things that are asked. Write the equation is the first thing we have to do to answer the second question, at least ideally. So here we have basically an x of 10 minutes traveled, of 10 minutes of time, of duration, and 3.5 miles traveled. That's an x and y. Time is x, distance is y. After 30 minutes, we've traveled 10.5 miles. So these are points on our graph, and assuming we do this constant rate, we want to come up with an equation that's modeling what we're doing. They said write an equation to model your distance. This says how far we travel based on a certain amount of time. So with these x's and these y's, what we're going to do is come up with an equation in what I want to use point slope form, because we have two different points we can get the slope. We can use either one of these points in this equation or both to make a slope intercept form equation out of it, because we don't have the y-intercept. So what we got to do is first find the slope. The slope is the rise over run, y2 minus y1 over x2 minus x1. How far do we go from 3.5 to 10.5? 7. How far do we go from 10 to 30? 20. So 7/20ths, that's also a decimal. Let's figure, I think I should know it. It's 0.35, I think. 7/20ths is, yep, 0.35. So whether we write it as one or the other, it's kind of up to us. 0.35 would be 0.35 miles per minute, right? That's the rate. Miles per minute, or 7 miles every 20 minutes. I don't know which one you prefer saying there. We ride, let's use the 0.35, because these have decimals here. My y-intercept might also be a decimal. So let's choose either point. Like I can choose 10 and 3.5 here. I can say y minus y1 equals m times x minus x1, like that. Now when I distribute 0.35 into there, I get y minus 3.5 equals 0.35x minus times 10 is 3.5 actually. And when I add 3.5 over, I get y equals 0.35x plus 0. That actually makes sense because for this thing here, it says you haven't traveled any miles at any time started, if that makes sense. At 0 minutes, you've traveled 0 miles. That's not always true because they might say, oh, you're 10 minutes away from, or 10 miles away from home. So they might have a plus 10 there to begin with. But this one is just directly proportional in that way. So there's the 0.35x. So there's the equation. That's the equation. Now it says, how far can you ride your bike in 45 minutes? If x is the amount of time, what we're going to do now is substitute 45 for x and figure out how much mileage that is. So 0.35 times 45 is 15.75. So you can travel 15.75 miles in 45 minutes. And that would be the answer to that. So we're using our model with that. That's the interpretation of everything that I had there. That might be it for the section. And that is. So now we move on to section 2.4. Now 2.4 is solving linear systems. So I'm going to have a lot to write, so I'll probably have to go on the next page for this after. As you can tell, they have a lot to write for a single problem. And we have 6 problems to do here, plus another word problem with this. So we're going to live in this one for quite a while, it seems. Solving linear systems. Solve the system. They have this system here. I'm just going to leave it as it is. And your goal is to turn a system of 3 equations into a system of 2. That means get rid of one of your variables using either substitution or elimination. Depends on the problem. This problem looks prime for elimination method. Find a variable to get rid of. And then when you do it among the 3 equations to make a system of 2 equations, so then you can get rid of another variable, things like that, if you know your methods. Let's see which method they did. They said add equation 1 to equation 3 to eliminate z. So their goal is to get rid of their z's. Z minus z is 0. By that, I literally mean z plus negative z. Meanwhile, they're going to add x and 4x to get 5x. They're going to add negative y and 2y to get 1y. So 5x plus y equals, and negative 3 plus 2 is negative 1. Z's are eliminated. Then they're going to eliminate z's in another set of equations. So it looks like they're taking the third, let's see which one they're doing. Second equation and they're taking the first equation. They're taking the first equation and multiplying it by negative 5. I would have personally taken the bottom equation multiplied by positive 5 to keep the signs as there. Multiply this by negative 5 here times negative 5, and then you get a rewrite of that equation. And this will eliminate z's though, because negative 5z plus 5z is 0. But this adds to negative 3x, this adds to 4y, and this adds to 19. Now you have a system of 2 equations here and here, which only have x's and y's in them. And our goal is to now eliminate another variable to solve for one of them. So it looks like they're going to eliminate y. They're going to take this equation and multiply by negative 4 to do the same kind of thing. Get an additive inverse, get negative 4y here, positive 4y here. The y's will eliminate. These add to negative 23x. These add to 23. Divide by negative 23, you get x equals negative 1. Now you got to substitute negative 1 for x and say one of these 2 equations right here to solve for y. I'll let them kind of, they don't even show the work, so I'll just let them assume. Like 5 times negative 1 is negative 5. Add 5 to both sides, you get y equals 4. So they got x equals negative 1, y equals 4, and now they can substitute that into any equation to solve for z. They chose the top equation here to solve for z. Negative 1 for x, 4 for y. Combine those, get them over to the other side, you get z equals 2. So our final solution with x equals negative 1, y equals 4, z equals 2 is written as an ordered triple of negative 1, 4, and 2. So that's a nice example in that all the values are integers. It's only one single solution. We might see problems where we are going to get infinitely many solutions, in which case we got to do more work to talk about dependency on one variable. We might get a no solution case. That'll probably be the fastest type, but I still got to explain what it is when it pops up, if it does. And there are problems where we'll probably use the substitution method here and there. And some problems might have fractions as answers. So that's the part where it gets a little tricky. All right, let's start with number 12 in solving the system and checking your solution if possible. Number 12 has x plus y plus z equals 3. Negative x plus 3y plus 2z equals negative 8, and x equals 4z. Now, with the nature of this problem, the way that it's already written to start with, I'm more attuned to probably using the substitution method here. The substitution method, x is already by itself, and this equals 4z. Let's let 4z substitute for x in both of these equations right here. So we're actually going to create a system of two equations with only two variables. X will be completely gone. You'll only be left with y's and z's. So my equation 1, instead of x plus y plus z equals 3, will be 4z plus y plus z equals 3, because 4z replaced x. 4z plus z is 5z, and here's now a new equation, number 1. Equation number 2, I'm going to substitute here. There's a negative on the outside, so be careful. That's negative 4z plus 3y plus 2z equals negative 8. Combine those and you get negative 2z. So 3y minus 2z equals negative 8. Now I have two brand new equations that I can use in a system, here and here. Let's do kind of what they were doing in a one-stop shop kind of way. Let's multiply this top equation here, say by negative 3. And what I'm going to do in multiplying by negative 3 is it turns this y into a negative 3y. My goal is to eliminate these y's here. And that's minus 15z equals negative 9. Everything gets multiplied by negative 3. Now this guy I'll bring down here as well. We get 3y minus 2z equals negative 8. So let's add down these lists and see what we get after that. The y's eliminate. Negative 2z minus 15z is negative 17z. And negative 8 minus 9 is negative 17. Divide by negative 17 on both sides, you get z equals 1, which is a nice integer value. We got one of our solutions for our system. To solve for y, we now got to substitute 1 for z into preferably one of these equations here. How about that top one? Y plus 5z equals 3. So y plus 5 times 1 equals 3. 5 times 1 is 5. Subtract 5 from both sides, you get y equals negative 2. Now we got to solve for x. Let's use the x plus y plus z equals 3. Oh, let's use this one. X equals 4z. X equals 4z, and 4 times 1 is 4. So our final solution needs to be written as an ordered triple, however. The x goes first, then the y, then the z, like that. That's the final answer you should be writing. This is where three planes are intersecting at a single point. That's the part that we're actually indicating. What is the actual x, y, z value that works for all three equations in the system? It's this one. Now, I didn't double check anything, but I'm just going to go ahead and say the numbers look good. I'm going to trust it. Okay. We're going to move on to, give me one sec. Okay, we're going to move on to number 13. We have 2x minus 5y minus z equals 17. And I need to stress a couple things here. First of all, this will take a while. If you note, when I did this actual video, I think it was one of the 3+ hour videos because there were so many system things to do, number one. Number two, there's more than one way to solve each problem. But there should only be one unique solution to the problem. So even if you do this problem a different way, you should be arriving at that answer, assuming my answer is correct. Same thing with any of these. What I choose to do is my own choice, and it's up to you if you want to do something different. I see a reason I could eliminate x, y, or z, and I'm going to use the elimination method this time. The reason I'm going to choose to use z is because there's already one that's set up to eliminate without any extra work. I can add equations 1 and 3 together right now, and hopefully you can kind of see what I'm going to do here. Add equations 1 and 3, negative z plus z is going to eliminate, becomes 0. But I do 2x plus negative 4x, I get negative 2x. Negative 5y plus 6y is positive 1y. Those eliminate. And 17 minus 20 is negative 3. So there's using equations 1 and 3. If I want to eliminate z's in another one, I could take the top equation and say multiply it by 3, because then I'll get negative 3z with this 3z right here. And that'll become 6x minus 15y minus 3z equals 51. Now if I align that with the second equation, x plus y plus 3z equals 19, I can add down those lists. I'm going to write it down here. It's a modified 1 with equation 2, but I am going to eliminate in the process. 6x plus x is 7x. Negative 15y plus y is negative 14y. The z's are gone, and 51 minus 19, no, plus 19? 51 plus 19 is 70. What I also see in this bottom equation is everything has a multiple of 7. So if I divide everything by 7, it'll just get a cleaner look for me. Divide by 7, I'll get x minus 2y equals 10. Now that top equation is negative 2x plus y equals negative 3. So let's choose which variable we'd like to eliminate here. Why don't we eliminate the y's just because I already manipulated this equation once. Now let's manipulate this equation once. Let's multiply it by 2. That'll get rid of the y's because I get negative 4x plus 2y equals negative 6. So y's will be gone as x's remain. I get negative 3x equals 4. Ooh, do we get a fraction answer here? Negative 3x equals 4, so x equals negative 4/3. All right, I trust my own numbers. I think everything I did has been fine, even with the division by 7. So x equals negative 4/3 is one of my answers. I'm not going to round it, and I'm going to accept it for what it is. I would double check, not me, but if I were you, I would double check work and make sure that a fraction is what we expect. Because I've seen fractions from them before, I don't doubt it. So 4/3 goes in for x, or negative 4/3 goes in for x in one of your equations to solve, say for y. How about this one? X minus 2y equals 10. So I'll do x minus 2y equals 10. If you're already sick of the fraction like I am, I can multiply everything by 3, make it 3 times bigger, and we'll get negative 4 minus 6y equals 30. And solve for y here. Fully expect a fraction on y. Negative 6y equals 34. Divide by negative 6, you get y equals negative 34/6, which can reduce to negative 17/3. Once again, something with the thirds in it. Now z, we have to use the negative 4/3 for x, negative 17/3 for y in one of our equations. I guess this bottom one. How about this one? This x plus y, because it's already kind of, those are nice for x and y. So that is, I'll use purple over here. X plus y plus 3z. X plus y plus 3z equals, and I think it was 19. 19. Now I will multiply by 3, but first I can combine these because they have a common denominator already. So negative 21/3. Oh, look, that'll actually work out. Negative 21/3 plus 3z equals 19. Negative 21/3 is negative 7. Okay, I don't need to multiply by anything extra. Now, I'll probably still get a fraction for z's answer. 3z equals 26, so z equals 26/3. Okay. And there's my order triple. Negative 4/3 for x, negative 17/3 for y, and 26/3 for z. And this is, again, among the reasons why we're only the second problem in on this. And there's also the example. But this is why this kind of, took so long, right? We have some things to do, basically, right? We have some things to do. Okay, that's number 13. Let's go to number 14. On number 14, we got x plus y plus z equals 2. 2x minus 3y plus z. All right, kind of crunch the data a little bit there. I'm not offended by eliminating z again. I just feel like it's best set up for it. I can take either of the top equations, and both of them. I can take both the top equations and multiply them by 2. If I multiply the top equation, like this one and this one, I can eliminate them with the bottom equation, just like that for each of them. So I can multiply the top equation by 2 times 2, and I'll get 2x plus 2y plus 2z equals 4. Merge with the bottom equation here. Just keep it the same. Negative 3x plus 2y minus 2z equals negative 13. The z's will go away here. So z's are gone, and we're left with negative x plus 4y equals negative 9. Now, if I take the bottom equation times 2 again, I can eliminate z's with that. The middle equation times 2, I can eliminate z's with the bottom equation. 4x minus 6y plus 2z equals 22. And then this guy right here, keep it the same. Negative 3x plus 2y minus 2z equals negative 13. Now, the organization of these problems can get a little scattered because I'm just teaching it and, color coding and stuff like that. I can't guarantee that my scatter would look perfect if you, say, wrote this all in pencil and then you look back at your work and say, what the heck was I doing? So I apologize if the flow is kind of but we're good, hopefully, as I progress through this. Okay, look at these two. These are quite interesting together. So this one has negative x plus 4y equals negative 9, and this has positive x minus 4y equals 9. When it comes to elimination, folks, everything here is going to eliminate when I add right down the list. What does that mean? It means we get 0 equals 0. What does that mean? It means all variables eliminated and I get a true statement. This is a case where you have an infinite number of solutions. Infinitely many solutions, I should say. But I'm actually not done, because what we want to do in a system of 3 is we want to express the other variables in terms of one of our variables that we have. So this is part of our answer, but we're still going to write an ordered triple in terms of one of our variables. I'm going to go ahead and probably just get x by itself here. It seems like it's already set up to go. If I add 4y to both sides in this equation, I'll get an equation that says x equals 4y plus 9. Now what I'm going to do with this information is the following. Y is basically now the variable that I'm depending on. It's the independent, but it's the one that I'm depending on to make my other variables run. So basically, when I write my ordered triple, remember it goes x, y, z. My x is going to be 4y plus 9. My y is just going to be y, and z is going to possibly also be based on y. Maybe the y's will cancel, or maybe they'll be part of it. But if it's based on y, I'm going to write it there. If it's just a single number, I'll just write a single number. How do I figure it out? I substitute 4y plus 9 is x, and y is y, into any of the equations with z, such as the top equation, x plus y plus z equals 2. Or should I say, hold on a second, or should I say x plus y plus z equals 2. We're going to solve for z in terms of y as well. It's possible the y's cancel. It doesn't look like that's the case for this problem. So let's try that out. 4y plus y is 5y. If I subtract 9 over, I get negative 7. And now I subtract 5y over, I get z equals negative 5y minus 7. So that's z's value here in terms of y. The basic premise of an infinite number of solutions for a set of three-dimensional planes is that they're all either intersecting at a whole plane, or in this case, intersecting to form a line. And we're basically constructing what this line looks like. Meaning I could plug in a number for y like 0. If y is 0, then x is 9 and z is negative 7. If y is 1, then x is 13 and z is negative 12. Right? So those are points that are on this line in 3D space. Not that we see what the graph looks like, but this depends on this, and that's the infinitely many solutions there are. It can be anything on this thing depending on what y is. And that's the one that I chose to use. It's, you can do whatever, but that's what I did. Okay, let's go to number 15. We got x plus 4. So I'm expecting a no solution one at some point. I don't know if it's going to be this problem or any of the next couple problems. The word problem, I expect just one solution, which would be fairest of all if they did that. Okay, let's see if there's another variable I should eliminate. I don't like the look of eliminating z this time. I'll tell you that one straight up. And I generally won't use substitution unless it's forced on me or unless it seems best to use it. And right here, it doesn't seem to be the case. Eliminating z seems terrible as far as multiplying things to get there. X seems best here. And it seems like kind of the same thing as I did before. I should multiply this equation by negative 2 to eliminate with this one, and maybe this one by negative 2. Or you can do something like this. We can do something like multiply this equation here by negative 1. And if I multiply it by negative 1, what's going to happen is all these signs are going to change to negative, 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 negative. Can you imagine? I'm not saying like, oh, could you imagine? I'm saying, can you imagine these being negative here for a moment? Because what I'm going to do is eliminate the x's with the top equation and middle equation. So with equations 1 and 2, I'll get x minus x, which is 0, 4y minus 3y, which is 1y, negative 2z minus 7z, which is negative 9z, and 3 minus 1, which is 2. Now what I could do is I could multiply all these ones by 2. Remember, they were negative here. Now if I multiply them by 2, now it'll be negative 2x minus 6y minus 14z equals negative 2. And actually, let me change the color on that because I'm going to write it down below as I do the elimination with equation 2, a modified equation 2, and equation 3. Notice now these can eliminate the x's. So a modified 2 with 3, 2x minus 2x is 0, 9y minus 6y is 3y, negative 13z minus 14z is negative 27z, and 2 minus 2 is 0. Now right off the bat, 27z, Right off the bat, I'm seeing that these are 3 times bigger than they need to be. I could divide them all by 3. But even furthermore, if I'm looking to cancel out a variable, I could say cancel out y's by dividing by -3. That'll give me negative y plus 9z equals 0. And gasp, what are you seeing here? You're actually seeing a y minus y, which is 0. Negative 9z plus 9z is 0. 2 plus 0 is 2, but you get an equation that says 0 equals 2. So this is actually that next case that we want to refer to, the next special case. What happens when the variables cancel and the left side doesn't equal the right side and all your math is right? This is a no solution case. No matter what I substitute for x, y, and z, I will never get the left side to equal the right side for all 3 equations together. There is no one point or line of concurrency for which all 3 planes intersect, even if 2 of them do somewhere. There is nowhere where all 3 of them will intersect together. This is a no solution case. We're actually done there. We don't do anything after that. We just go on to the next problem. And I will. Number 16. So on number 16, if you can tell the middle equation, whoopsie, I just lost. The middle equation doesn't have a z. That means it's probably best that I can try and eliminate, z's in one of the other ones. So let's try that. So number 16, I got x minus y plus 3z equals 6. X minus 2y equals, and I like to do the spacing here like that to just show the missing z. And 2x minus 2y plus 5z equals 9. It doesn't mean it's best to eliminate. Actually, I probably don't want to eliminate z's. That's not too fun to try and eliminate these ones. So let's try something else here. Let's do eliminate x's or y's. There's no one that's better than the other. Because the y's are already negative, let's go with x's. Right? Let's force some negative as we need to. Let's do kind of what we did last time. Let's multiply this one by -1, so change these signs, negative plus and negative. So we'll have 1 and 2 combined together. X minus x is 0. Negative y plus 2y is 1y. And 3z adds with nothing. Unfortunately, I don't get to take advantage of this not having a z. 6 minus 5 is 1. Now I'll do the same thing as I did it's literally the same thing from the previous problem. Same format, probably not a no solution case though. Now let's take all that and multiply it by 2, given that it's negative. So negative 2x plus 4y equals negative 10, and add it with equation 3. So modified equation 2 with equation 3. 2x minus 2x is 0. Negative 2y plus 4y is 2y. I got that plus 5z equals -1. Okay. So now that we combine, well, we don't combine down these lists. Now we got to do some stuff with this one. I don't see substitution on the horizon for the next problem, so let me do a substitution form here just for a brief moment. I'm going to solve for y in this equation by writing it as 1 minus 3z, subtract 3z over. And I'm going to take this 1 minus 3z and substitute it for y in this equation. This will be a way to get z by itself in its own equation to solve for z. Yes, I could use elimination. I can multiply the top equation by -2, get rid of y. I just want to show you a different format here for a second. So instead of 2y, I'm going to write 2 times this, like that. And now I can distribute the 2. And then combine like terms. Negative 6z plus 5z is negative z. And subtract 2 and divide by -1. So z equals 3. I'd argue that's longer in substitution, but what it does do for me, at least here in solving for y, at the very least is y is already by itself here. Y is 1 minus 3z. 3 times 3 is 9, so y is -8. That was a little faster. X was not by itself in any of my equations up top, but let's substitute them in. 3 and -8, and let's use this middle equation. X minus 2y equals 5. Remember, that's what it originally was. X minus 2y equals 5. I'm going to take advantage of not having z there. X plus 16 equals 5. X equals -11. So my final ordered triple here is -11, -8, 3. -11, -8, 3. That's the one that you ultimately box as far as like, look here, right? That's what we had as a whole. All right, we still have one more before the word problem. So number 17, like I said, I don't think this one's really set up for substitution either, not as a whole. But there is no y term here, so let's see if we can eliminate y's most easily on this one. Number 17, I got x plus 2z equals 4. Putting a placeholder there so that I can get y's kind of together. x plus y plus z equals 6, and 3x plus 3y plus 4z equals 28. Okay, because y is gone right here, I'd love to do something to eliminate the y's here. That means I'm going to take the middle equation and multiply it by negative 3. Let's get negative. Oh, look, the x's will eliminate too. Minus 3y minus 3z. I don't know why that took me a while. Equals negative 18. So this is really nice, actually. This was incidental, but it worked out. We're actually going to solve for z. We get z. This is going to be really fast. We get z equals 10. We get z equals 10. Now I have this, so forget the system of 2. We can now just go to this equation with 2 variables here, and let's solve for x. X plus 2 times 10, x plus 20 equals 4, so x is negative 16. All right, that was fast. And now solving for y, let's use that equation. X plus y plus z, negative 16 plus y plus 10 equals 6. That's y minus 6 equals 6, so y equals 12. All right, that was the fastest of them, just possibly by happenstance. I don't know if I just lucked out in what I did or if it would have been fast no matter what I did. But negative 16, comma 12, comma 10, we got that system of 3 correct. All right, we have one more here, which is a word problem. Now, on this word problem, we're going to have to come up with our own system of 3 based off the information, and then we'll solve that system of 3 as a result of it. So, a school band performs a spring concert for a crowd of 600 people. The revenue for the concert is $3,150. There are 150 more adults at the concert than students. How many of each type of ticket are sold? So there are 3 different equations we can write. One for the number of people. What is it? Students, adults, and children under 12. By the way, you probably can't see this sign very well, so I'm going to copy and paste it. Hopefully it's not too blurry. It's a little strange because it's very red. Can you see that? It's a little blurry, but it's also very red, so I apologize for just its appearance. But this shows more information that we actually need. It's not just an image of like a stock photo. We actually have to use this information. So this information shows the different kinds of people that there are, and it's actually best that you define your variables. I'm going to use X, Y, and Z for students, adults, children under 12. So I'll have, let's let X equal number, what we're trying to find, how many of each type, number of student tickets sold. Y is number of adult tickets sold. And Z is number of, I'll just say children. Number of children ticks sold. Well, child ticks sold. But child under 12. That part doesn't actually matter as a number. But anyway, those are the different types of tickets that were sold. Right? I guess if you're 12 or older, then you're an adult, unless you're a student. So let's come up with those 3 bits of information. The first equation I'm going to do is just the 600 people. There are 600 people total. Therefore, we can add X, Y, and Z, and we get 600. That's one equation, just based on number of tickets sold. There's also a money equation. The money equation is the revenue for concert is $31.50. This is where we use this information. $3 per student times the number of students gets you how much money you made off students, 3x. $7 per adult times the number of adults is right here. And is that 2? I think it's 2. $2 per child times the number of children, 2z. And total, you get $3,150. So that's the second equation. The third equation is a comparison of 2 things. There are 150 more adults at the concert than students. So the number of adults, Y, equals the number of students plus 150. Now, people tend to kind of make a mistake there. Sometimes you'll add 150 to the Y instead. But there are 150 more adults. The number of adults is 150 more than the number of students. So now we're going to say how many of each type of ticket are sold. We're going to solve for X, Y, and Z. This one I'm probably going to use substitution for because I have this Y equals X plus 150 here. So I'll go ahead and substitute that in for Y there and substitute that in for Y there. Create a system of 2. So instead, in that first equation, I'm going to have X plus Y plus Z equals 600, or rewritten as 2X plus Z equals, subtract 150, you get 450. So there's one equation. Keep that in mind. The second equation is going to be a little bit bigger as far as numbers go. We got 3x plus 7y. You got to use parentheses. Plus 2z equals 3150. This might be one of those equations, though, we can like divide by something. Let's see. 3x plus 7x plus 150 times 7 is 1050. Plus 2z equals 3150. 3x plus 7x is 10x. And 3150 minus 1050 is 2100. So yeah, I can divide these at least by 2. So divided by 2, and you get 5x plus z equals 1050, I think. Hope I'm getting that all right there. Now, the z's can cancel if I multiply one of these by -1. Let's take this equation here times -1. And then that will go down here, and you get -2x minus z equals -450. So this can get us to now solve for x. We'll get 3x. Let me fix that line. We'll get 3x equals, looks like 600. Therefore, x equals 200. Now we're on our way to solving for y and z based off x being 200. Let's go to z next. Let's do this equation where we have 2x plus z equals 450. So 2x plus z equals 450, or 400 plus z equals 450, which means z equals 50. We'll interpret all this in a second, guys. Our final answer will not be an ordered triple. We're going to use context. We have words. We have definitions for these variables. Now, y, you have, let's use this one. Y equals x plus 150. The simple one. Y equals x plus 150, which is 350. So, you could, it's best that you like triple check all this to make sure it works for all three equations. I'm not going to. I'm just going to assume I got it. But here, what are we saying? X is the number of student tickets. Y is the number of adult tickets. Z is the number of child tickets under children under 12. Tickets for children under 12. So, to answer the question, instead of an ordered triple, we'll say there were, how many are sold? There are 200, I almost want to say were, this looks weird. There are 200 student tickets sold, 350 adult tickets sold, and 50 tickets sold for children under 12 years old. And that's our final answer there. Those should add to 600 with the prices in mind. They should add to $3,150. And apparently there are 150 more adults than there are students, which is kind of the way I got that last number. All right, that's number 18. That is for that section. Let's move forward as we're way over an hour in. We still have 3 more sections to go, which could have the longest problems. I don't know. Section 2.5, transformations of quadratic functions. Now 2.2 was transformations of linear and absolute value functions. So this is just the quadratic version of that, if that's the only kinds of questions they have. Let the graph of g be a translation 1 unit left and 2 units up of the graph of f of x equals x squared plus 1. Write a rule for g. So, by the way, and I'll state this after we do this problem, but this is also where we really started to do a lot of vertex form equations too. I think they introduced us to it. I think they also said, we're good with you graphing out of vertex form without a table. So get ready for us to maybe do some graphs. Anyway, the transformed, here we go. So 1 unit left is where we take our f of x and we add 1 to it. I know they wrote minus -1 because they're thinking all vertex form like, but that will be a plus 1 inside there. And we're also going to translate it 2 units up. Remember, the original equation was x squared plus 1 though. So when we do f of x plus 1 and then add 2 on the outside, remember of the x squared plus 1, our g of x will be taking wherever x is and replacing with x plus 1. There's the plus 1 from the original equation right here, and then the plus 2 comes from the other transformation. Translate 2 units up, goes right there. 1 plus 2, I was going to say 1 plus 2 is 3, but they have a 4 because they're skipping some steps in between. Here's what they're doing in between on this problem. As they said write a rule for g, there was nothing that said they had to write it in standard form, but they did. So I don't know if we had to do that. But so, one version of this thing would be vertex form. G of x equals x plus 1 quantity squared plus 3. Whoops, that got cut off. Plus 3, right? But they went into standard form after. Now let me show you what they did. It was 2 more steps. They expanded x plus 1 squared. So they wrote it as x squared plus 2x plus 1. And then this plus 3 adds with the plus 1 to get 4. So now they have g of x equals x squared plus 2x plus 4. So when they said simplify, there were actually 3 more steps that happened, or at least 2 additional ones that happened in between. And they get that final answer. I'm kind of good with the vertex form version as well. So unless they say that you must simplify or write it in standard form, or the original, I guess the original's in standard form, but you could also argue it's vertex form. So I think either or fits for that one. Okay, there's the example. There's the transformation with stuff. It kind of reminds me of the 2-2 information. Let's go to our problems. Number 19. We got problems too, you know. Number 19, describe the transformation of f of x equals x squared represented by g, then graph each function. So this is not the same type of question as the example. This is one where we already have the transformation in the equation, and we are going to do the graph. Now this one is the x plus 4 being inside of there. That's a transformation. It's a translation, excuse me. The graph of g is a translation 2 units left, or 4 units left of f. I'll just say of f. To us, you know, we really start, and this is actually where I use this different kind of graph paper because we know they're all quadratics. I want to kind of get as tall as I possibly can. So I'm going to copy paste this one. And I think we found out that these graphs are actually taller than they're wider. Oh well, we're going to keep them as they are. But anyway, this is where we also started to use some vertex form graphing. This equation literally is in vertex form. The vertex is at -4, 0. Maybe you recognize that first. Maybe you graph that first. And then you come up with the description. Either way, and they're not requiring we graph the parent function, it looks like. It says graph each function. Yeah, I'm not going to graph the parent function. I got a vertex of -4, 0. That's the only change. Other than that, we should be going 1, 1, 2, 4, 3, 9, 4, 16 upward. I think in section 2.6 we start doing the axes of symmetry, so I'll leave it for now because it's just more work and more time on me when we don't have to do it. But this is that parabola of g of x. See, the original f of x would have been the same thing, except what? It would have been translated 4 units. You know, it would have been right here. So we're 4 units to the left. Boom. There we have it. All right, let's go to number 20. 20 and 21 are also in vertex form, so I'm not going to pretend like they're not. I might even do the graph first and the description after. I think it's worth that we understand both forms of it. G of x equals x minus 7 quantity squared plus 2. Not to say that vertex form ain't doing anything that the transformations don't describe and vice versa. Because when I say that the vertex of this thing is at 7, 2, I'm also saying take your points, translate them 7 units right and 2 units up. So 7, 2 is the translation of not just my vertex, but all my points. That's why I do everything in relation to the vertex. The vertical stretch factor is 1, so we keep the status quo. 1, 1, 2, 4, 3, 9, and 4, 16. Now, 16 up from 2 is 18. That would be just above this. This one kind of goes beyond there. I'll make shift that it's there. But keep in mind, if you run out of window range, you run out of window range. Sometimes you just kind of stop what you're doing. So maybe I just only do it up to here and I say stop because I didn't actually have enough room to plot the rest of it. It's not that it's asymmetrical. It's that we just didn't have enough room to fit it. So describe the transformations here. The graph of G is a translation 7 units right and 2 units up of F. All right. That's it, and that's all for number 20. Let's go to number 21. And this time we have a stretch factor, vertical stretch factor. And it's doing a little bit more than that as well. It's got a reflection piece to it. So number 21, g of x equals -3 times x plus 2 quantity squared minus 1. So, once again, whether I do the graph first or the description first, it should apply to the same way. We do have a vertex. Now remember, if I talk about vertex here first, it doesn't mean I describe the translation first. But we do have a vertex of -2, -1. So I'm going to start with that. -2, -1. But the a value is -3, which means 2 things to us when it comes to the description and the graph. It's flipped over. We're already keeping in mind it will be flipped over. And everything's going to be 3 times taller than it was. But I'm already at my affixed vertex. That's why we have to describe these first. But I'm going to graph this. Over 1, not up 1, but down, not 1, but 3. 3 times bigger. And instead of over 2, down 4, we're going to go over 2, down 12. Okay? 12 is 4 times 3. So 12 more than -1 is -13. So right here and right here. And that's all I could fit. If I went over 3, I would have gone down 27 instead of 9, and over 4, I would have gone down 48 instead of 16, all that kind of stuff. 3 times more than normal. So it is a vertical stretch of 3. It is a reflection in the x-axis, yes, yes, and then it's a translation. I translated first because I knew I was going to stay there, but you have to describe it last here. So the graph of G, is a reflection in the x-axis and a vertical stretch by a factor of 3 from F, followed by a translation. This is everything. Followed by a translation, 2 units left and 1 unit down. Keep in mind we should do the reflection and stretch before we actually do the translation, even though I graphed it with the translation in mind first. That's my tables graphing format, and there you have it. All right, let's go on to numbers 22 and 23, where we write a rule for G. I think these will be more like the example that they had. So, number 22, let the graph of G be a horizontal shrink by a factor of 2/3. There's a lot more I'd have to explain here. I'll try and keep it brief. Followed by a translation 5 units left and 2 units down of the graph of f of x equals x squared. Maybe I'll do an in-betweener here. So we have f of x equals x squared. Let's do an in-betweener called h of x. And let's do that with the horizontal shrink, so we're not bogging us down with other things. So h of x equals, it takes f of x, but we're going to do a horizontal shrink of factor of 2/3. Now, keep in mind, horizontalness goes inside the function because it's a stretch or compression component. It's going to be a multiplication of, but you do the opposite of what you see here. Instead of 2/3, you do not negative 2/3, but 3/2, because our x's need to be 2/3 the size of what they are to compensate for the fact that we have a 3/2 here. So what we're going to do now here is h of x will be 3/2 x will replace x, so 3/2 x squared. Whoops. 3/2 x quantity squared. My personal preference is to not have this horizontal shrink inside of here, but instead turn it into a vertical stretch by doing what? Squaring the 3/2, turning it into 9/4, and the x is still squared. What was inside of this representing horizontal shrink is now outside of it because it's not in parentheses anymore. 9/4 is multiplying by x squared. So this is now a vertical stretch by a factor of 9/4, 2.25 times taller than it was instead of just 2/3 times smaller in this direction. They both mean the same thing, but that's how I'm writing it. So that's a simplification of that portion. Now followed by a translation of 5 units left and 2 units down of this function. So a translation of 5 units left will look like this, and 2 units down will look like this. So we'll take the h of x equation, and where you have x, we're going to change it to x plus 5. So we got 9/4 times x plus 5 quantity squared, and then outside of there is a minus 2. That should be the final answer. There is a version of it that you can keep 3/2 inside of there. I would prefer not to. I hope you're understanding of kind of why I'd prefer that. And that's what it's going to be. That's what it's going to be, folks. Beep, 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 beep. Here's the other thing as to why you probably don't want, when you replace x with 3/2 x, that 3/2 x is going to be the thing where the x plus 5 goes into. You'd have to put x plus 5 in parentheses on that part after as well, right? If you're doing the other version of it, let me write it. If you're doing the other version of it, this x plus 5 would be in parentheses right here. Whoops. Which would be appropriate. But now you're dealing with that. So you either have that as an answer, or you can distribute the 3/2 like that. I don't know what a book might say on one versus the other. I know they're big on simplification. Maybe they turn it into standard form. I don't know what they do. Either these are acceptable. I really don't like the bottom one, because at least this one still has some version of vertex form. At least your vertex is at -5, -2. This one doesn't even reveal that. So I really don't like that one as a whole. My favorite really is this, a times x minus h quantity squared plus k. And I hope that you're wise to know why, that you're feeling out why I'm really recommending that. It seems most appropriate. Turn horizontal stretches and shrinks into vertical shrinks and stretches if you can. All right, let's go to number 23. Let the graph of G be a translation 2 units left and 3 units up, followed by a reflection in the y-axis of the graph of f of x equals x squared minus 2x. Okay, there's every reason in the world that you really want the interim here, especially considering the fact this is in vertex form. I'd want this anyway. So I'm really going to hunker down, start with the translation, then do the reflection. That's another reason order of operations will matter. So the original equation is f of x equals x squared minus 2x. We're going to put something in the interim called h of x. And here's what we're going to do. Translation 2 units left. So that's an x plus 2 inside the function. And a translation 3 units up, that's outside the function. So what this is going to look like now is we're going to replace x plus 2 in for x anywhere we see it. So x plus 2 squared minus 2 times x plus 2. And then there's a whole plus 3 that's hanging out on the outside. This one goes here. These replaced x. We want to simplify this thing. This is what the book would have done as well. X plus 2 quantity squared is x squared plus 4x plus 4. Negative 2 times x plus 2 is negative 2x minus 4. And there's a plus 3. Combine like terms. This is just the translation parts, by the way. Combine like terms. You have x squared. 4x minus 2x is 2x. 4 minus 4 plus 3 is 3. So x squared plus 2x plus 3. This is just the translation parts. Now let's do a reflection in the y-axis. Let's call this one g. That's what they're saying. So for g, we're going to take our h of x equation and we are going to change the sign to negative x. That doesn't mean so we're going to replace every x with a negative x here. That doesn't mean change every term into negative though, because we have negative x quantity squared plus 2 times negative x plus 3. So the plus 3 doesn't change, and negative x quantity squared is positive x squared. So this becomes x squared minus 2x plus 3. Here's the new equation. This is one of the ones that I'd love to confirm with a graphing calculator. I'm not going to, but this is one of the ones where it's like, did this actually do what I wanted it to do? That we would go over 2, up 3, and then it goes over to the other side of the y-axis. We could check it. Am I going to? I don't think so. I think I'm just going to leave it as is and trust that my stuff is good. All right, let's go to section 2.6 on characteristics of quadratic functions. This is where we do start to talk about axes of symmetry. We start to talk about mins and maxes, all that jazz. Let's see what we got going here. This snapshot just stays on the screen. Okay. They have an example. We graph f of x equals 2x squared minus 8x plus 1. Oh, by the way, we're hitting some standard form and intercept form. This was a big section. We had like 84 questions, I think, on it. Label the vertex and axis of symmetry. So we've done some vertex form graphing already. Let's see what standard form's all about. Standard form, we use this negative b over 2a biz to find the axis of symmetry. The axis of symmetry is the vertical line that crosses through your vertex. So when we find the axis of symmetry, we also find the x value of the vertex. When we find the x value of the vertex, we're going to plug that into our equation to find the y value of the vertex. So a is 2, b is negative 8, c is 1, as they write right here. Negative b over 2a is the formula for finding the x value of the vertex, or the axis of symmetry, and they get 2. So x equals 2 is the equation that this graph crosses through. Remember, you don't have the graph yet. This is pretending like this is the first thing you're able to do. You're able to come up with that line. On this line exists the vertex, where plug in 2 for x in your equation. Do f of 2. 2 times 2 squared minus 8 times 2 plus 1 is negative 7. So your vertex is at 2, negative 7. That's a point that we get on this thing. Now, another point we can get on this thing, and they mention it, they have the y-intercept at 1. We know that our constant in a standard form is going to be the y-intercept at 1. That means this is a point that's on this graph. Because we have the axis of symmetry, we can also note that any point that's some height is also going to have a corresponding point the same distance away from the axis of symmetry at that height. So if this is 2 away from the axis of symmetry, there's a point that's on this other side that is. So that's an easy point to obtain without any calculation or counting whatsoever. Well, counting of 2. But from there, I would apply the stretch factor. The stretch factor is 2. They said plot a point. I'd forget that. I'm going to use the stretch factor of 2 and go over 1 up 2. Boom, get a point and reflect it. Over 2 would be up 8 instead of up 4, and this confirms that there's that point as well. And of course, if I can fit more points, I'm going to. I'll also go over 3 up 9 times 2, which is 18. So that's how we graph that one out of standard form. That's among the different ways that we can do that. Labeling the vertex, boom. Axis of symmetry, boom. We got them labeled. We'll do some more of the same. So let's go ahead and do numbers 24 to 26. Now, not all of these will be in standard form. In fact, the first one's in vertex form. The next one is in standard form, and the final one's in intercept form, or as I like to call factored form. Or factored form as they like to call intercept form. So number 24, and we've done graphs of this sort, so let's just do one again, but then we got to do labeling of vertex axis of symmetry. They have some more questions of that beyond it. Let's see what they say. Label the vertex and axis of symmetry, find the min or max value of f, and describe where the function is increasing and decreasing. Sorry about that. Okay. Done a lot of talking. Normally these reviews last an hour or less. This one's going to be pushing the 2-hour mark easily. Okay, graph the function. I'm going to do that first. We've seen a lot of these before, and we ain't stopping now. So, the vertex is at 1, -4, HK. The axis of symmetry is the line x equals, and then the x value of the vertex, 1. So when it comes to plotting this, we're at 1, -4, like so. The axis of symmetry will be the vertical line that goes through there. That's what x equals -1 is. So it looks like this. Boom. You like to make it a dotted line to say it's not actual points on the graph. It's just a way to describe your graph. Stretch factor is 3. We just saw that a bit ago, a problem ago. We're going to go over 1 up 3 and reflect across this axis. We'll go over 2 up 12 because 12 is 4 times 3. So I think that's 8 up from there, 8 up from -4, and then reflect that across. And I would go over 3 up 18. What's 18 up from -4? Is that 14? 18 up from -4? No, 27 up. 27 up is 23. Okay, we can't fit that. Sorry, it's 9 times 3, not 9 times 2. So I'll still draw this graph as is, like so. They said graph the function. I'm doing it. I've already called out what the vertex and axis of symmetry are. It looks like they did labels with the actual numbers. What I've been doing in the problem set is I've just been calling them what they are, like this is your vertex, this is your axis of symmetry, and I hope that's okay. Now the graph will help tell us some other things. They don't ask for domain and range, but they do ask for the minimum or maximum value of f. Now I could have answered this before I did the graph knowing what the vertex was. Because this is a positive number, it will be upwards facing, and because it's upward facing, the vertex is at a bottom. The bottom makes a minimum. So this has a minimum of its y value. The minimum is -4. They're asking what the y value is when it comes to minimum. Now the increasing or decreasing part is more about x based on what y is doing. So the increasing decreasing thing is saying, hey, this thing is going down to the left of this x value, the axis of symmetry, and it's going up to the right of this thing. So decreasing here, increasing here. Note, these are not parts of the graph. I'm just doing some labeling for you. So let me actually point all that out. I'll make it a little more transparent like that. So it's increasing when x is greater than 1, the axis of symmetry, and it's decreasing when x is less than 1. They might say those in words. They might say it's decreasing to the left of x equals 1 and it's increasing to the right of x equals 1. I think this is probably a better say in what you're doing because this is more common to what you'd be doing in some like calc classes and stuff like that. You might also use what's called interval notation, which is not what I did there. Anyway, that is everything I had to do for that problem. Let's move on to number 25. Now, number 25 will be following a little more closely to the example we have because that was in standard form. This too is in standard form. So we got g of x equals -2x squared plus 16x plus 3. Okay. So for this problem, I'm actually going to, we got to find the vertex, and we'll be doing that. First thing I'm actually going to do is pay close attention to that 3. This 3 is the y-intercept. It's the value of y when x equals 0. That's true in standard form. You can reveal it. So I'm going to plot that first just for good knowledge of it's there. So I want to make sure you know it's there. And when we find the axis of symmetry, we'll reflect a point across and just say, hey, that was a point that we got to find for ourselves. Don't forget that that's one that's there. Anyway, the axis of symmetry is the next thing I want to find. It is the equation of that line where x equals -b over 2a. They have that written on the other side of the page there. So -b over 2a. That's -16 over -4, which is 4. So the axis of symmetry is the line x equals 4. That's my official detailing of it. This is going to be my official labeling of it right there. That also means there's a point on the other side of this graph. This is 4 away from the axis and on the same height as another point 4 away from the axis. I'm plotting this graph without having my vertex. I need my vertex, but I'm plotting some points without it, which is cool. By the way, this will be a downward facing graph, make note with the negative, so it's going to do something like this. And hopefully, fingers crossed, here's the thing, guys, I think this vertex is going to be a little bit tall. I think it's actually going to be beyond the reaches of this graph, so I might actually end up changing the scale of this graph. So let's just pay close attention to that, see what happens. Now, to find the y value of the vertex, I have to substitute 4 for x, and I'm going to get negative 2 times 4 quantity squared plus 16 times 4 plus 3. So this will be 16 times negative 2 is negative 32 plus 64, which is positive 32, plus 3, which is 35. Yes, so this vertex is at 4, 35, which means I need to change the scaling of my graph. I need to change the scaling of my graph in such a way that this graph's y values only go up to 17. That's my own personal graphing stuff, and if you're using mine, you might want to follow along. That means I probably got to go by, listen, we can go by different things here. I'm going to go by 2s. I know that 17 times 2 is 34, which means it just goes beyond the reach of this thing, but that also means I got to shrink these twice as much. So, because if I'm going to go by 2s, that makes this 10 and 20 and 30, right? Which makes 35 just out of reach, halfway, right? 32, 34, and half of that's 35. That's fine, though. I can use that. But these will be 3, right? 3 is halfway up between 2 and 4. So this is the point 0, 3, right? And this is 8, 3. These, by the way, guys, are also negative 10, negative 20, and negative 30. And I'm keeping my x scales at, 5 and negative 5. So I'm keeping these by scales of 1 instead these are scales of 2. So now when I do the graph here, I now got to apply stretch factor. I know they're going to say plot points in a table. I'm going to go over 1 down 2, over 2 down 8, over 3 down 18, and over 4 down 32, which is actually already plotted. But remember, because these are scaled by 2s, then down 2 is technically down 1. So over 1 down 1 will peg me at this 33 height, right? Over 1 down 1. Unfortunately, I'm halfway between points. That's just the nature of what I have to do. Over 2 down 8 is technically over 2 down 4. So now that I'm scaled by 2, so now my count is the same I would always count. Over 3 down 9, 5, 6, 7, 8, 9 is like that. And these should technically be the over 4s down 16. I think those will fit. I want to fit one more as I feel like I'm able to. Over 5 down 50. In this case, I got to count 25 down from here. But 50, let's try this. What's 35 minus 50? Negative 15. So here's 10, 12, 14, 15 right there. And that's the last one I can actually fit. One of the taller graphs that we've seen, even with a compression of 2, or, we're scaling by 2s on y, it's still one of the taller graphs that we're going to be making together here. Totally. If you do it the same way that I'm doing it there. If you use the same graph paper, or at least you're hopefully getting the understanding of how I chose the graph the way I did. Now, we still have some more things to do. I got to label vertex, axis of symmetry, nice. Okay, what we also have to do is identify the min and max and where this thing is increasing and decreasing. Now, because this is a downward facing graph, this one now has a maximum, and that maximum height is 35. That is the y value of it. It is increasing all the way up till, not up till, as we move to the right, the graph increases all the way till x equals 4, and then it decreases after x equals 4. So it increases for every x value that's less than 4, and it decreases for every x value that's greater than 4. Because it's downward facing, that's the nature of what we're going to do. And that fills out number 25. Okay, now let's go to number 26. Last question of this set. That was just trickier because the scaling, we had a little bit more to do. But hopefully the example problem also covered up enough of what we had to do as a whole. H of x equals x minus 3 times x plus 7. Now, this book has not had us do a lot of transformations. Like, I can make this into standard form, and I can complete the square and get it into vertex form. I could do all that stuff. We did that more in IM2, actually, by the way. None of the stuff we're doing isn't unlike what we did in IM2, except for the increasing, decreasing thing. But this is intercept form, and this form has its benefits as well. It doesn't give you the vertex, not off the bat anyway, but it does give you the x-intercepts. When y equals 0, the x value, x-intercepts are values of x and y equals 0. When y equals 0, if x minus 3 equals 0, x equals 3. And if x plus 7 equals 0, x equals negative 7. It's kind of the opposite of what you see there, assuming this is true intercept form. So when we have the x-intercepts, it's like that. By the way, there would ideally be an a value that's factored out of here. The a would have been right here, but because it's not showing up, it must be a 1. That means we have a stretch factor of 1. This is a positive upward-facing graph. We'll do the conventional 1, 1, 2, 4, 3, 9-bit. But let's start with what we have here, x-intercepts of 3 and negative 7. Now, I personally prefer plotting these first because the next thing I like to do is find the axis of symmetry, and generally I like to do it from the graph, meaning the axis of symmetry is always halfway between. It's the midline between any 2 points that are of the same height. X-intercepts are of the same height, and these are 10 away from each other, right? This is 10 away from each other. So halfway between is 5 away. What's 5 away from here, 5 away from here? That guy right there, x equals negative 2. So I have my axis of symmetry at x equals negative 2, and I like to use my graph to do that. Now let's say you didn't graph it yet. Let's say you don't know how to do that, or let's say you don't like to use the graph to do that, or let's say the numbers are just weird, lands you on a decimal. How could I then find the axis of symmetry? I would find the axis of symmetry by averaging these two values. The x, it's an x equals, and we average these by adding them and dividing by 2. That's negative 4 over 2, which is negative 2. So that's me officially marking my axis of symmetry at x equals negative 2. Hope that makes sense. And we drew the line. These 2 points reflect across each other. Awesome. Now, the x value also is the value of the vertex. The x value of the vertex. Excuse me. The axis of symmetry is also the x value of the vertex. So to find the y value of the vertex, we got to substitute negative 2 into our equation, and we're going to get negative 2 minus 3, which is negative 5, times negative 2 plus 7, which is positive 5, and negative 5 times positive 5 is negative 25, which is another uh-oh for us when it comes to scaling and fitting this point, because the vertex is at negative 2, negative 25. My graph only goes down to negative 17. It appears that, one more time at least, we're going to have to scale by 2's on y. So this will be negative 10, negative 20, and negative 30. Looks like negative 25 will be right in between there, so right here. So this will be a little bit trickier for me to plot the points. I'll call them out as we do them in just a moment, and we'll go 10, 20, 30 over here. 10, 20, 30. The x's are still going by 5 or by 1s. I hope that's okay. So 5 and negative 5, yada yada. Okay. So there's the vertex, there's the axis of symmetry. Let's just plot some points to graph, and then we'll answer the rest of the questions on the minimum and the increasing and decreasing. Now, like I said, this is a stretch factor of 1, which means we get to go 1, 1, 2, 4, etc. But these are crushed twice as small. So when I go 1, 1, I do go over 1 on x, but I go up 1/2 on y. 1/2 up is 1, right? And over 2 up 4, that's 1, 2, 3, 4, like that. And these are on halfway marks as well, unfortunately. Over 3 up 9, 2, 4, 6, 8, 9 is just another half with that. So it looks like all the odd numbers are going to land on integers, which is kind of nice, but I don't really count it that way. Over 4 up 16, so 10. So let's see, 11, 13, 15, 16. Hope you're okay with how I'm describing this. Over 5 up 25, it looks like that's what this one is here, right? From negative 25 to 0, that's 25 up. I'm still going to fit some more, guys. I'm going to try and do as many as I can really plot on here. Hope that's okay. Over 6 up 36. 36 up, this is where I kind of just do some math now. 36 up from negative 25 is 11, and 11 is halfway up after 10. Like, if that makes sense, because 12 is this guy. Over 7 up 49. 49 up from negative 25 is 24. So 24 is 22, 24 right there. And I think that's probably the last one I can fit. I don't think 8 up will fit on there. So another super tall graph that is yet also compressed in its own right. We didn't do a lot of, I mean, this is not technically a vertical compression, but we kind of drew it like one, but we didn't have many vertical compression factor quadratics, did we? I don't recall actually doing any actual vertical compression factor ones. So consider this one to be an instance of like having a vertical compression factor of 1/2. We went over 1 up 1/2 instead of 1, over 2 up 2 instead of 4. It's like that equivalent part. All right, 2 more things to answer within this. We want to get the minimum, which this has as it's upward facing. The minimum's negative 25, and this is increasing to the right of our axis of symmetry. It's decreasing to the left of it. So when x is greater than -2, we're seeing an increase. When x is less than -2, we're seeing a decrease because it's going down as we go. It's really as we go to the right what happens. And by the way, that behavior is something we're going to speak on a lot of when we hit the next chapter on polynomial functions in intervals where something's increasing or decreasing. I assume that's what they're going to ask. All right, last section is 2.7, modeling with quadratic functions. Let's see what example they call out. This should be a lot like the 2.3 section of linear functions, only for quadratics. We make equations for quadratics. We can make them in standard form, vertex form, or intercept form based on the kind of information we have. We can also use scatter plots and data to come up with information. All right, let's look at their example. The graph shows the parabolic path of a stunt motorcyclist jumping off a ramp, where y is how high they go and x is how far they go in feet. Write an equation for the parabola, and then they say the motorcyclist lands on another ramp 160 feet from the first ramp. What is the height of the second ramp? So the first thing is they give us some information. They give us the peak of their jump, the vertex, the maximum, and they give us another random point. Whether it's y-intercept or otherwise, it's another point. From this, we can come up with a vertex form equation of this parabola most easily. That's the one that I'd most recommend here. So 80, 30 is like your hk in your form. They're kind of bringing that up right now. The x minus h plus k, 80 for h, 30 for k. Now, they're not writing an in-between that I generally tend to want to write, which is kind of plugging those in first. So it would first look like y equals a times x minus 80, quantity squared, plus 30, oh no, plus 30 like that. I do this in saying all I need to find left is a, and I'm going to temporarily substitute an x and y into here to figure it out. So you know what you're going for, right? We need to find out the a value. Now they're going to plug in 20 for x, or 20 for y, and 0 for x, and solve for a along the way. They square -80 to get 6,400. They subtract 30 over from 20 to get -10, and they divide by 6,400, and they get a is -1/640. So now their final equation of this will look like this, that models the motorcyclist's jump path. And then they also come up with a domain. They didn't yet establish how this domain is provided. So the ramp. I guess the ramp that they hit is 160 feet from there. After that, the model's done. So I guess that's why they do that. But they said find the height of the second ramp. So what they're going to do to find the height of the second ramp is, the second ramp's 160 feet away. They're going to substitute 160 for x and find out what y is with this model. So they're going to do 160 plugged in for x. 160 minus 80 is 6,400. 6,400 divided by -640 is -10. -10 plus 30 is 20. And they get a height of 20 feet for that second ramp. So using the model, they can do that. There are a lot of different questions they can ask for us with that in mind, but this is just among them. Let me also point out the way that I generally come up with these equations, or the stretch factor, is I figure out, my 1, 1, 2, 4, 3, 9. I know that we're going down instead, so I know it'll be negative. Instead, I'm going over 80. Normally, I'd go down 80 squared, which is 6,400, but now we're going down 20. That's where I come up with that whole we're going down 10 from 30 to 20. So that's where I say 6,400a. I take 6,400, I multiply by my stretch factor, I get -10. I get to that part without this extra fluff. And we can still come up with that answer of -1/640. That might be confusing to you guys. I understand. But I'll still talk about it if I think it's relevant to the problem. Vertex form, it will be relevant. So if we have a problem like that, like number 27, I'll probably do the same thing. All right, this is a context-free question here on number 27. It does ask us to write the equation of the parabola at the given characteristics. It has a vertex of 10, -4. I'm eyeing vertex form as a for sure. It's got a point that it passes through that is 1, 12. And without actually drawing the graph as a whole, they just said write the equation. So this is our hk. And with that in mind, that means our equation is going to look like some sort of y equals a times x minus h quantity squared plus k. Now what I need to do is find the a that's associated with that by plugging in this x and this y into the equation. So I can substitute 12 for y, 1 for x, and I get that 1 minus 10 quantity squared minus 4. I'm going to add 4 to both sides to get 16, and here I get -9 quantity squared like that. -9 squared is 81, so 81 times a. Divide both sides by 81, and you get a equals 16 over 81. And I don't think that can reduce there. So I'm going to go ahead and just write that out as y equals 16 over 81 times x minus 10 quantity squared minus 4. Very strange equation. They don't ask us to do anything else with it, so I'll leave it at that. One other thing I'm just going to mention, probably not going to be a very pretty version of this one. Actually, I can't assume any of this will actually be pretty on this one, is that normally when I go over, oh geez, this would actually be a very crazy one to look at for this. Normally when I go over 9 from 10 to 1, I'm going over 9. Normally I'd go up 81. So, but now I'm only going up 16, right? I'm going up from -4 to 12. So that's where I do the whole 81 times a is 16, and that's where I solve it. That's where I get my answer there, or my answer there, I should say. Okay, so that's the equation of that one at number 27. Let's go and move forward to number 28. And this time we are not going to use vertex form. So they didn't do an example like this one. Of course, the whole section did, and they only do so many examples. That's why we have this problem to do. So we have x-intercepts of -1 and 5. That sounds a lot like we should be using intercept form for this one. And we have a point that we cross through that is 4, 3. Remember, this is the xy we can use for a question like this. So with this in mind, we are looking at intercept form, which is y equals a times some x minus p times x minus q, like that. We're going to use our intercepts there in intercept form, use those to solve for a. So let's plug in 4 for x, 3 for y. 4 plus 1 is 5. 4 minus 5 is -1. We get 3 equals -5a, and a equals -3/5. What I like about these problems is I'm good in accepting what that kind of answer is. It's a strange one, but since we're not graphing it, since we're not doing any other questions based off it, the fraction is all, and then we just write the problem, and we're good. I mean, I don't have to do anything else with it. We're taken care of. That's it. So that's number 28, intercept form. They're not asking for a specific form, so I'm going to use the form that's best for us in the problem, that's most conducive to our information. Number 29 is something where, well, we got to use standard form. And it's good that we get a problem like this, right? So -2,7 is a point, 110 is a point, and 227 is a point. Now, standard form has a different look, right? Standard form is ax squared plus bx plus c equals y. We have to, not bx squared, just bx plus c. We have to find a, b, and c. We don't know any of the information yet. All of these points are just whatever they are. Now, the y-intercept isn't one of these. If we did know it, we could plug that in. But we don't know any of them. So what we got to do, and I'm going to rewrite this as ax squared plus bx plus c equals y. I'm going to plug in this number for x and this number for y and make an equation out of it. So a times -2 squared is 4a, plus b times -2 is -2b, plus c equals the y value, which is 7. Now I got to do it for this problem, or for this ordered pair. A times 1 squared is a, plus b times 1 is b, plus c equals 10. And then for this one, 4a plus 2b plus c equals 27. This becomes a system of 3 for which we got to solve a, b, and c. So that's what we're doing with this stuff here. Now, normally I'd like to eliminate c. It would be the easiest one to do. In this case here, b actually might be the easiest because we already have one that can add down the lists, 1 and 3, right now. If we add 1 and 3 right now, they eliminate. So we get 8a, these cancel, and then plus 2c equals 34. And if I multiplied the second equation by 2, boom, 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 then I can add with the first equation there. So 1 with a modified 2 will give me 6a, b's cancel, plus 3c equals 27. Now, both of these equations I can make smaller. You know I like to go smaller instead of bigger here. I'm going to divide this one by 2 and get 4a plus c equals 17. And divide this one by 3. Heck, let's divide it by -3. Let's get rid of one of these things right now. We'll get -2a minus 1c equals -9. This will eliminate my c's as I go down the list here, and I get 2a equals 8, therefore a equals 4. So I solve 4 for a, or I solve a equals 4. Let's plug it into an equation like this top one, 4a plus c equals 17. 4a plus c equals 17. And it looks like we're getting c equals 1. And now we can use these to solve for b. Use any equation that you like. I like the a plus b plus c equals 10. So a plus b plus c equals 10. That's b plus 5 equals 10, or b equals 5. Now, we're not going to write our answer as an ordered triple. Remember what this was. These were parameters for our standard form equation y equals ax squared plus bx plus c. we want to substitute them into there and write our equation. This is the one that's going to model the one that goes through these 3 points. So y equals ax squared, that's 4x squared, plus bx, 5x, plus c, which is 1. That is the parabola that goes through those 3 points. It's a little trickier. It's a lot more work, but that's the best way to do it. It's the best way to do it. It might be the only way to do it outside of using a calculator. All right, number 30, and this is the final question, and we're going to be long of 2 hours. The table shows the heights y of a dropped object after x seconds. Verify the data shows a quadratic relationship. Write a function that models the data. How long is the object in the air? So it looks like number 30 is going to be another kind of question that, well, it's going to be quadratic. This time thing makes me believe that this will be a negative 16x squared equation. I can already tell you 2 of the bits of information right here, I bet. I just don't know what b is yet. But I'm not going to go off that. These are just predictions I'm going to make. The easy prediction is this is clearly the y-intercept. See, you can look at the point 0, 150 right there. So you can see that that's one of them. My guess is based on gravity and feet and seconds, this is a number that you'll almost always see. So get ready for that. Anyway, let me copy and paste that table because what we have to do is show that this is actually indeed quadratic. How is it quadratic, or how can we tell it's quadratic based off the information? Because the distance between any 2 y values, the difference I should say, should have a constant difference in and of itself. We call it a constant second difference. Now these intervals for x are constant, even though they're going by halves. We can still go by that and say, hey, you see how this is minus 4 and minus 12 and minus 20 and minus, I'm bad at this, minus 28 and minus 36? Well, the difference between negative 4 and negative 12 is negative 8. From negative 12 to negative 20 is negative 8. And all these have a constant difference of negative 8, the constant second difference. This is how we know it's quadratic. This is what quadratic functions do. They have a constant second difference. Now, am I going to use that negative 8 stuff with this? Not entirely, no. What we are going to do, though, is come up with a quadratic equation based off 3 different numbers. Now, I'd prefer to use the integer values, not the decimal ones, so I'm going to use these ones here. I think I'm just better off using them. And we're going to do the same thing we did last time, coming up with the standard form equation, y equals ax squared plus bx plus c. We're going to write a system of 3. Now, the first equation will be easiest. A times 0 squared plus b times 0 plus c is just leaving c by itself, and you get an equation that will say c equals 150, which makes sense. This will be our y-intercept for this one right here. That's what we can write. So I'm automatically going to solve using substitution by plugging in 150 for c in the next 2 equations I write. I'm going to plug in 1 for x here and get a plus b plus c equals 134. Now I'm going to plug in 2 for x and get 2 squared 4a plus 2 times b plus c equals 86. So this is now technically just a system of 2 equations I'm focused on. Let's keep working this one out, clean it up a little bit. Subtract 150 from both sides on this equation, you get a plus b equals negative 16. And in this equation, I have 2 things I want to do. I do want to subtract 150. 4a plus 2b equals negative 64. But then I want to divide everything by 2. In fact, I want to divide everything by negative 2. Divide by negative 2. And let's bring that down here because I'm going to straight up eliminate right now and get negative 2a minus b equals positive 32. So we're going to solve for a with this information. B's cancel out. You get negative a equals negative or positive 16. Therefore, a equals negative 16. And remember, I expected that value here. It's just a gravity thing. It's just a general expectation. I still haven't found b, though, right? That was the whole goal. I have c. I have a. I need b. Let's use the equation a plus b equals negative 16. So negative 16 plus b is negative 16. So b equals 0. All right. So the equation y equals ax squared plus bx plus c is y equals negative 16x squared plus c, which was 150. Now, if I read the word problem, I would have known that was it because it says an object is dropped after x seconds. Dropped. That means this is the maximum height it'll hit and it'll only go down from there. That means there's no horizontal translation. That means there is no b. So I should have known this was the answer before doing anything. You wouldn't have known that, and we have to do all this work still, but I should have absolutely known this would have been a 0. Oopsie, should have really read the problem and comprehended it. Anyway, we got more things to do. It says write a function that models the data. We got it. How long is the object in the air? Well, you have to understand the domain. The domain goes from x greater than 0 to something, right? I don't know what it hits eventually, but I don't care about time before 0 seconds. So when I solve for x in this quadratic, when I set y equal to 0, how long is it in the air? I only care about the positive x answer. Just keep that in mind. I'm going to subtract 150 over, divide both sides by negative 16. You get positive 150 over 16 is whatever. I take the square root of that. It's square root of 150 over 4. Well, really it's plus or minus, right? But here's the thing. We're only going to consider the positive answer there. Now, this is a time where we go to the calculator. Go to the calculator and we do square root of 150 over 4. And get out. Whoops, what is that? That is not a square root. Square root of 150 divided by 4. And we get this number here, 3.06186. I'm just saying 3.06 seconds. That's how long the object is in the air. The negative part doesn't really matter to us, like I stated, because that's something that's beforehand, before the object was dropped. That's not part of the model. So the object is in the air for 3.06 seconds. Does that make sense with our information? I think so. You can see it starts at 150 feet. At 2.5 seconds, it's at 50 feet, and it seems to be dropping very fast and progressively. A little bit after 3 seconds, it looks like it's going to kersplat. As it's increasing its speed, as it goes more and more. You have to keep in mind that the next time we hit 3 seconds, that's going to be at minus 44 from here. So it's going to be at 6 feet. Excuse me, at 3 seconds. No, I got rid of everything. Minus 44, because that's 8 seconds less than the previous one. At 3 seconds, it'll only be 6 feet in the air. So 3.06 seconds is very believable and very trustworthy for an answer. And that's the last question. All right, guys, that ought to do it for this one. This is Mr. Robinson. Thanks so much for watching. One of my longer reviews, but also it's one of the more comprehensive ones. Compared to the quiz, if you remember it, that one didn't seem to have as much stuff that was covered as an overall. What are the things that were skipped here? Yeah, of course. It's 30 questions versus the hundreds of questions that we did as a whole for the entire chapter. But this is a pretty good review, and I really wanted to slow things down and mix things up and talk about different aspects of them. And hopefully that really, really helped everything for you. If there was a one-stop shop to look at what to do with this chapter, this 2+ hours would have been the one to look at, I suppose, if that makes sense. Of course, you had to know some things beforehand, but for problem set practice, this one is it. Make sure you have the graph paper stuff downloaded and ready to go, and all good there. We're still going to do a chapter 2 test and cumulative assessment review, and we'll see if those questions are good, surplus, additional, enriching ones. I remember from the chapter 1, those were actually kind of harder problems, so let's see if there are harder problems for you as well. Thank you guys so much. Take care. I will see you in the next one.